Good evening, Taylor Tots. Video number 3. As promised, I wanted to talk a little bit about using KMT and really talking about why gases really do what they do under certain conditions. Again, we've talked a little bit about these conditions before, but again, nothing wrong with the review. The conditions of a gas are going to come down to pressure, volume, moles, and temperature. And those are the things that can influence a gas readily. With temperature, I really kind of wanted to take a little bit of time to take a step back and really kind of look at what the heck temperature is. A lot of people think it's this notion of temperature being hot versus cold. And it's kind of what we've discussed in class. That's completely false. Temperature does have a relation to what we believe is hot outside and what we believe is cold. We've discussed this in class. Cold doesn't exist. And actually, I challenge you guys. Hashtag cold doesn't exist. Add me on that, okay? I want to see kind of how many people are watching this video. I want to see if we're getting the point across. So really, challenge you guys. Hashtag cold doesn't exist, okay? Add me. See what happens, okay? Just a little experiment. But really what it's concerned with is temperature is related to the speed of the particles. So I might not have done the best job showing it, but I really kind of wanted to use these arrows as kind of a way to represent how fast the particles are moving. A big arrow implies that they're moving super, super fast. And as you can see, we're getting lower and lower. And one of the really powerful things about this is you can kind of see where we're going. This is kind of what gases do. A little bit closer together, not moving as much. Liquids, and of course going down here, solids, very close together, vibrating in place. So I really kind of just wanted to kind of go through that. So for example, I got a bunch of markers right here. Solids are going to kind of be like this. They're going to be here, but again, they're going to be moving just back and forth, just kind of like this, not really moving that much. And as the temperature goes down and down and down, they move less and less and less until they hit a point of no movement, which we call absolute zero, which we talked a little bit about as well. But again, you start adding heat. Particles are going to be moving faster and faster, and then all of a sudden they're kind of like a liquid. They're going to be kind of flowing around each other, nothing kind of crazy. So this would be a liquid. Getting close together, not too far. And then gases. Gases are going to go absolutely crazy, as you can absolutely imagine. But that is kind of an important thing to realize, is gases are going to be crazy. Gases are unpredictable. They move in straight motion. And we kind of go from there. So let's start actually mentioning into KMT, because that's a great connection to that. Again, KMT, or kinetic molecular theory, explains a little bit about why gases do what they do. And it comes into 4 parts. Number 1, we assume that gases have no volume and no attractive forces. We discussed in class that that's obviously impossible. If we have that dot, and you know gases are way, way, way smaller than that dot, it still has a volume. And I could take this scope all the way out, and I could take it to the point where you can't even tell where that dot is anymore. You can you? And if you can, I'll just keep backing it up. There's a point where you can't see anymore. But that doesn't mean it's not there. Gases are the same way. They're really, really small, and they kind of work their way through there. This allows us to do a lot of easy calculations, including the ideal gas law. When you get to college, you'll kind of talk about more advanced laws where we don't pretend anymore. But right now, we're good. 2, Gases move in random linear patterns. You can't predict where they go. Kind of like all those markers I just kind of flicked around. There's no way of you possibly knowing where that is. And we can continue from here. Collisions. Perfect. Elastic. Okay. And, you know, I was really kind of trying to think, you know, what I could show you guys that could be a collision. And I actually have something that might work here. So, going up here, my wife made this like paper star jar. As you can see, it's just a big old teddy bear kind of thing. But let's check this out. If I collide with this with my thumb, and it's going to be a little tight because this plastic's a little thicker, but I'm still going to show you. As you can see, trying to get to an angle where you can see it. Yeah, I can push that in. If I do this enough, I would puncture through this plastic. This is not elastic. This is inelastic. It is not able to bend through. This is not what gases do when they hit each other. Gases perform more like this. And again, we know that with the figure 8 kind of that we mentioned in class, but what we can do is this. If I send, or if I have these two pen caps, and I smush them together, there's nothing happening. There's no smush. That is what gases do. The only difference is they also don't slow down. So when gas particles move, it's 80 miles per hour, 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 80 miles per hour. They're not going to slow down. In the real world, if we were going 80 miles per hour, it would crumble and stop. Gases don't do that. They hit and keep going. And again, those of you that remember us going outside, we demonstrated that with pool balls, which is a great way of looking at it. And I'm going to post a video underneath where you can get a little bit better of a visualization of that. And of course, first thing we kind of mentioned, but kind of just wanted to review it. Kinetic energy is related. Is related to temperature. The more energy something has, the more it's moving, the higher the temp. Which is why if you get these particles moving super fast, we might get like maybe 120 Kelvin, something like that. A little bit lower, 50. A little bit less movement, 10. It is all directly related. And we can use these to really kind of help us out with a few ideas. I'm going to take a second just for you guys to pause that. I'm sorry I got a little crunched at the bottom. Give you guys a little bit of a second to do that. And again, I really wanted to then focus in on a little gift I have for you guys, and that's going to be this box. So, pressure. This is a set volume, right? I'm not changing the size of this box. Volume is set. But really what kind of happens, what comes down to it is this idea of pressure and collisions, okay? When you have something like this, particles are going to be moving very quickly. Trying to show that here. But you guys can tell, well, particles are going to hit each other pretty good. You know, and this idea of pressure really comes from these two ideas. Pressure comes from either a lot of collisions happening at the same time. That's an example of a high pressure, where this might be a low. Or you can counteract that with the force behind it. For example, this would not be a high pressure. Whereas, same marker, this is. Or this. Think of it like that. When you think pressure, I want you to think collisions. So, if you can imagine, right, if the particles are moving faster, with a higher temperature, they're going to be hitting more. Okay, if you're running through the hallway, you're going to hit more people than not running through the hallway. Okay, that's a true statement. You know, if you have a lower temperature, the particles are going to be moving less. It's like you walking through a crowded hallway. You're going to be able to dodge a lot more things. You're not going to be hitting people as much. And that makes sense. And that makes sense. When you really kind of start to squish the volume, make the volume smaller, you're increasing the number of collisions because they're closer together, right? If I had all these particles, right, going back to this, if I had all these particles and they easily, and I know I'm not showing this 100%, so I apologize. If I have all these particles just randomly here, right, there's plenty of space for them. Do I have space to fit all of these nicely in this corner? No, I wouldn't. And for that reason, they would hit each other a heck of a lot more. A heck of a lot more. And those 8 particles, even though that they might still have their speed, and if you allow me, I accidentally just ripped the visualization I was going to show you guys. My bad. So you can imagine that is going to hit a heck of a lot more than all 8 of these being spread out. So just really wanted to kind of mention some of that stuff about KMT. Kind of wanted to definitely mention temperature a little bit. Again, I hope everything's going well for everybody. This isn't easy for any of us. This isn't getting easier for me, I'll be honest. But really just try to be engaged. Find those opportunities that are available to you. And again, I'm doing an experiment. I want to see how many of you can come up with this idea, hashtag cold doesn't exist, and at me. I just want to see how many people are watching the videos. Again, keep it together. Share these with everybody, okay? And we'll kind of go from there. Have a great one, Taylor Tots. Peace.